our last speaker, we are very fortunate to have Professor Sergey Levine. And Sergey is an assistant professor in the ECS department at UC Berkeley. He received his bachelor's, master's, and PhD degrees all from Stanford University. And his research focuses on machine learning for decision-making and control, with an emphasis on deep learning and reinforcement learning algorithms. Given his numerous impactful works that combine perception and control, we're very excited to have Sergey as an invited speaker in this workshop. And today, Sergey is going to talk about his research on scalable robotic learning. With that, I'll hand it over to Sergey. Yeah.
Thank you, Quan, for the introduction. My screen is visible and it's all on the right slide. Okay, perfect. Okay, so actually, a lot of what I'm going to talk about is going to echo some similar, philosophical ideas as what Saurabh discussed in terms of how to pull in more data into robotic learning. So to start off with a bit of motivation, and this is probably something that's going to sound pretty familiar to a lot of you, when it comes to building robotic systems that utilize perception, that carry out complex actions, we have pretty good techniques for building robotic systems for closed world environments like factories, but things start getting really difficult when we move to open world settings. And of course, this is true for home robots, for things like disaster relief, maintaining and repairing electronics, what have you. And a lot of this is because the real world is very complex. There's a lot of variability. A lot of times robots in open world environments will encounter situations that they did not see before, and they need to generalize. And to a very large extent, what we call intelligence is really about flexibility. So when we say we need more intelligent robots, what we're really talking about usually is we want more flexible robots. So to give an example that I use in my reinforcement learning class, if you want a giant oil tanker to navigate halfway around the world, well, we actually have pretty good techniques for doing that. Like, if you use satellites and some basic planning algorithms, you can actually solve this problem. But if something breaks in the engine room of that giant oil tanker, then you need a person to go in there and like tighten a screw with a wrench or something. So it's like the nitty-gritty, hands-on, messy stuff is where you need the most intelligence, the most flexibility, and that's because that's where you have to deal with the unexpected. So a little vignette that we can think about to kind of give us a sense for the sorts of problems that will arise when we put robots in open world environments. Imagine that it is in the year 2031, so 10 years from now, and you've purchased your first home robot. Maybe it looks like this or what have you, and you task that robot with cleaning up your bathroom. So you put it in the bathroom, you tell it make this bathroom clean, and then you go to work. And your bathroom is very unfamiliar to this robot. So while you're away at work, maybe it does its best, but it messes up. It like spills a bunch of water on the floor and has to spend the rest of the day cleaning it up. And when you come home in the evening, yeah, it's like a little bit cleaner, but it's not great. And then on the second day, it's going to work a little bit more. It's going to try to figure out exactly where everything is. And maybe you come home in the evening on the second day and the bathroom is, a fair bit cleaner. And then by the third day, it's really figured it out and your bathroom is sparkling and then it succeeds every time thereafter. Okay, this is kind of, very much like what we imagine when we think about reinforcement learning, but of course it's not what actually happens in practice, right? The time scale is completely off. The level of generalization this demands is beyond what we can do today. So what are the pieces that are missing? What's the gap between where we are now and this little kind of vignette that I outlined for you? So we often think about learning robotic skills through the framework of reinforcement learning, because reinforcement learning is what formalizes automated acquisition of behavior. Traditionally, it's formulated as an active online learning process where you have an agent that interacts with the world many, many times and iteratively improves its behavior. And it's been quite successful in a range of domains, like playing video games, basic robotic manipulation tasks in laboratory settings, playing the game of Go. But if we look at the kind of domains where RL has succeeded side by side with the sort of domains where supervised machine learning methods trained on large and diverse data sets have worked out really well, we see that there's a big gap. It's not a gap of physical complexity. I mean, the RL algorithms are doing physically very complex tasks. It's a gap in terms of the difference between a closed world and an open world environment. So all the examples on the left are really closed world environments. When the RL agent is playing Go, it doesn't have to worry about someone knocking the Go board over or spilling coffee on the table. All the things on the right are open world environments where generalization is critical. So the differences are reinforcement learning is usually formulated as an optimization problem. How do you get the highest reward? Learning is often done in simulation and not much attention is paid to generalization. Almost all experience is collected online directly with the latest policy. And the result is that you get narrow experience that is non-representative of open world, real world tasks, and generalization is poor. In the state-of-the-art applications of supervised learning methods for tasks like computer vision, it's generally posed as a generalization problem. No one cares how well you do on the Emergent training set, just on the test set. Learning uses large real-world data sets, the larger the better. All data is previously collected, so there's a lot of data reuse. We start with large data sets that we got before instead of going out and collecting a new data set every time we train. And the result is that the data is broad representative of the real world and generalization is good. Of course, if you want to do passive perception, right? So can we get all the stuff on the right to apply to behavioral learning for robots on the left? I think the way that we should be thinking about this is not this kind of active loop that we usually see in RL, but something more like this recipe, where there's a big data set from past interactions, everything the robot has done before, so that home robot that you purchased to clean your bathroom, it's not coming in with no, with a blank slate. It's preloaded with prior data of lots of other robots that have cleaned other bathrooms in other homes. Maybe not your particular home, but a lot of prior data to give it a good starting point. And then very rapid, very efficient fine-tuning from additional interaction to really get the best possible performance in the desired environment. And that means that we need things like algorithms for offline learning, followed by online fine-tuning. And perhaps a more subtle point is that we really need algorithms that can master many different tasks, because the prior data is likely to be multitask data. And also in the course of performing a behavior in the desired environment, like in your bathroom, the robot might need to do many different things, not just to perform the task that you asked of it, but also to fix its mistakes. So if it spills the water all over the floor, now it has to deploy a different skill of cleaning that up before it can resume the task that you set for it. So multitask learning really needs to go hand in hand with this idea of leveraging large past data sets and adapting rapidly and autonomously to new tasks. So the three problems, and this is what I'm going to focus the technical portion of today's talk on, that I think are implicated in all this are, number one, reinforcement learning algorithms that can use broad and diverse data sets. Number two, leveraging the result of those reinforcement learning algorithms as a starting point to rapidly adapt to new tasks. And number three, learning many different tasks so that you can flexibly deploy the one that you need in the moment. So that flexibility that I mentioned before really requires a multitask setup. So I'll discuss a few projects today that get at different aspects of these problems. None of them offer a complete solution to all the parts, but hopefully you'll see that these kind of maybe comprise the jigsaw pieces that in the future could lead towards something that does all three of these. But so far, they'll be kind of in isolation or in groups. So let me start with something in the robotic navigation domain. So the problem that we're going to be aiming to solve here is get a robot to navigate to a goal indicated with an image. This is actually closely related to some of the things that Saurabh discussed as well. And the reason that we're doing this with an image is so that you can kind of ground things in the robot's understanding without any auxiliary information like GPS or ground truth localization. So everything has to be done from images. And so that means that the robot has its initial observation, it has a picture of the goal that it should reach, and needs to basically figure out what to do in between. And we're going to try to do this in a way that generalizes effectively. I'm going to show a lot of these kind of overhead views in this talk. When I show an overhead view, that's just for your visualization. That's not something that the robot actually gets. So it's just to emphasize the path that it took. We'll start with the first question. Can we address this problem in a way that leverages broad and diverse prior data sets? So if we have this robot driving around for a while, collecting lots of data, can we use that data scalably to train up a model that can solve a wide variety of these goal-reaching tasks? And then after that, I'll talk about how you can leverage this as a starting point to rapidly adapt to new tasks, in this case to new environments, obviously not cleaning your bathroom because it's a ground robot, but to navigating to new places and new settings. So let's start with the first part. The model that we're going to train is actually quite simple. it takes in the current observation and a photograph of the goal, processes both of them using a Siamese convolutional neural net, and then predicts two quantities: the number of time steps between the start and the goal, and the immediate action to take at the start. And this information can be actually obtained directly from the training data. So if you reached a particular state in your training data, then you can use that as an example, basically take any two pairs in the trajectory and use them for training. That by itself is not enough to actually solve more complex navigation problems, because this will basically give you a model that can reach things that it can currently see. So if it sees something in the background, it can drive towards it, but it won't figure out more complex navigational skills, like navigating around the whole facility here. This is a Richmond Field Station. More faraway goals, what we're going to do is we're going to construct a topological graph using the predicted distances, and these are temporal distances, right? So these are not distances in meters, these are distances in time steps. We're going to use them as edge weights on a graph where nodes correspond to previous observations that we've seen in that environment. So if the robot has a little bit of experience driving around this environment, you can think of the nodes as essentially landmarks, and edges connecting those nodes represent the robot's guess at how long it takes to go between any pair of landmarks. So then when you want to navigate to a new goal, you just connect that goal to the nearest node in the graph, nearest in terms of predicted temporal distance, and you predict your current, you connect your current observation to the graph, and then do a simple graph search, and then pick the action according to your model that will navigate to the first waypoint that you found. That's by itself, a fairly well-explored recipe at this point. There's a number of prior works that have tried to do this. What is interesting in this project to me is that all of this was done entirely using data that was collected before. So there was not a single episode of online data collection that was necessary to do this. All of the data actually even came from a different project that was done 4 months prior. So there's about 40 hours of training data that was leveraged for this. And I think this is very important, because this is how we're going to move towards more scalable robotic learning systems, by getting good at leveraging prior data sets, which will allow us to bring in a lot of diversity. So this data set was collected with the same robot, but during a different time of the year. Here in California, the grass gets a little bit more yellow in the summer, a little more green in the spring. So here's a demo of the system in action. Dhruv Shah, who's the first author on this, did a little kind of skit to illustrate the usability of this for kind of applications. So here is a pizza delivery application. You take a photograph of your front door and the robot brings you the pizza. This is a little like kind of patrolling application where you take photographs of different waypoints and the robot will drive around and patrol between those waypoints. And now in each of these cases, the robot does have some data, a limited amount of data in that environment to build a topological graph, but most of the navigational skills are coming from the prior data. So, okay, what happens if we now want to put this robot in a new environment that it's never seen before? And that's really going to get the second question. How do you leverage the model trained from prior data as a starting point to rapidly adapt to new tasks? Here is an example to illustrate this. Let's say that this is your current observation. So there's some white building in the background, and I tell you that this is your goal. Now you might guess that, well, you can't see that door, but it's a door on a white building and there's a white building back there. So maybe you need to drive towards that, but you should also search around a little bit to see if you spot that white door somewhere else. And that's what we're going to try to do. We're going to try to adapt this method so they can search around to find a goal, and in the process, rapidly build up a mental map of the environment that it's in. So in this picture, you can see the blue curve is a trajectory that the robot followed when it was searching through the environment, building up its mental map represented by the white nodes. And then once it's been built, then it can navigate to that goal again, shown by the red curve, very rapidly because it can reuse that knowledge. So that's really addressing that second question. How do you rapidly adapt to new tasks? So here's how we're going to do this. We're going to train a model that is structurally similar to the one we had before, except that now we're going to bottleneck the goal information through a latent variable that I'm going to denote as ZG. And this latent goal variable is implemented with a variational information bottleneck. So it has a prior on it, P0 of Z, and it has a posterior, which is inferred from the state and the goal. So if someone gives you a goal, you can get the posterior. If someone doesn't give you a goal, you can actually sample a random latent goal representation, which is very useful for exploring. So instead of saying take a random action, say go to a random goal. And then you predict the distance and the action like before, except that now you use ZG as the goal representation. So this is going to basically implement this kind of recipe that I had before for this particular navigation problem. So there's a big data set from past interaction that's used to train up this model. The latent goal variable will provide a way to rapidly explore in a new environment and then fine tune from a very modest amount of additional interaction, just about 20 minutes of additional interaction. But everything is still trained on the same exact offline data set. So even though the model has changed, we're still using the same 40 hours of data as before. And again, that kind of illustrates some of the power of being able to leverage offline data sets effectively in robotic learning, that the actual overhead in training this is comparatively not very high because you can reuse the same data. So here's what this looks like in action. You're going to see two runs now. The first run, the robot is placed in this environment for the first time, having never seen this environment before. And what it's doing is it's sampling random goals when it's on the frontier of its graph, basically when it thinks that it's near an unexplored region. When it is far away from an unexplored region, it samples a previous node that is unexplored. And when it sees the goal, then it will just go to the goal. And all this reasoning is actually done using the information bottleneck. So the way that it knows whether the goal is familiar or not is whether the embedding of that goal has a high probability. So it's kind of a graph-based exploration scheme that's directed towards the goal, but explores with random goals when it doesn't know where to go. That takes about 20 minutes. And using those 20 minutes of exploration, it builds up this mental map, this topological graph. And then on the second run, it can reuse that same mental map to navigate to the goal very quickly in about 20 seconds. So the adaptation is non-parametric in this case. It's done by building up this graph using the latent goal model. Okay, so that's kind of a little example of how such a system that uses prior data to pre-train a powerful policy and then fine-tune very quickly in a new environment, how that can be instantiated in the particular case of robotic navigation. But there's another piece to all this that I mentioned before, which is the need to do all of this in a multitask setting. Because especially for manipulation scenarios, you might want the robot to do a variety of different things, right? In navigation, maybe it's more straightforward. You just need to reach the destination. But in manipulation, you need a variety of behaviors. So let's talk about how we can scale up robotic manipulation with RL, and we'll actually arrive at solutions that in some ways structurally resemble the navigation example I gave before with goals and latent goal exploration, but obviously more elaborate and more multitask because of the need to handle manipulation skills. So the first work that I'll discuss builds on a system that we designed actually at Google about 3 years ago called QT-opt. So QT-opt was originally designed as a single task reinforcement learning system for real world robotic manipulation. It's a parallelized system for doing Q learning. And we initially applied it to robotic grasping tasks. So this is a single task setting where the robot's reward is just 1 if it grasps an object successfully and 0 otherwise. And I apologize, my video is a little glitchy there, but hopefully, yeah, that second one is playing a little bit better. The system works quite well. It works in a variety of different settings with different objects that are large, small, transparent, etc., and it generalizes to new objects, of course. But what I'm going to talk about today is how the same basic building blocks can be used to build a multitask system, a system that can perform a variety of different behaviors. And this is some recent work that we did called MT-opt. So the goal in MT-opt is to basically take that same large-scale RL system that already exhibits good generalization to different objects and get it to perform a variety of different behaviors. So the setup is that we're now going to define a variety of different tasks using these success detectors that are basically classifiers, and we'll reuse the same data for learning all the tasks together. So all of the data that the robots collect, regardless of which tasks they're attempting, is shared with other tasks and relabeled dynamically based on which task the robot concludes that data is most appropriate for. And that's done by relabeling it with each of the classifiers. And many of these tasks are kind of nested. So you could imagine that picking up an object is a successful example of picking up an object. It's also a successful example for picking up the particular type of object that you just grasped. So this generalizes QT-opt to learn multitask policies. There's 12 training tasks. The empirical results, which I won't go through in detail because I want to make sure to leave time for the goal condition stuff afterwards, but the empirical results do show pretty convincingly that sharing data across tasks in this way actually does lead to pretty substantial improvements in performance. And the system can then be used to rapidly fine-tune to new tasks. Kind of coming back to that bathroom example, if you have a multitask representation, that gives you an excellent basis on which to acquire new behaviors. So here is kind of a montage of different behaviors that can be acquired afterwards. So these are not the 12 training skills. These are other skills that the robot is doing afterwards. And you can see, some of them are like putting noodles in a bowl, dropping cubes into a bag, chasing a carrot that's running away for some reason. So it's kind of a wide variety of skills all around this theme of kind of picking and placing. So that's good. That means that the multitask angle in this is working. But we still have to work pretty hard to define those tasks with those success classifiers. So can we do something a little bit more like what we did in the navigation case? Can we automate task specification by taking a goal condition perspective on this problem? And this is what we did in this most recent work called actionable models. The concept is actually quite similar to what I discussed before for navigation. We're going to now give two images as input to the model, the thing the robot is seeing now, and a picture of the goal. And now there's no reward function at all. The task is defined entirely using a goal image. We have to use a more sophisticated reinforcement learning procedure to do this because the task is more complex. So we actually use a variant of something called conservative Q learning, which is an offline RL method that we developed. But the architecture of the model is similar, just a different training algorithm. In the manipulation setting, of course, this is more complex. You don't just need to drive to a location, you need to reposition the objects in the scene to match a desired goal image. And just like before, we're going to reuse the same exact data. So because this is going to be leveraging offline RL, we didn't actually collect any new data for this project. We just directly used the data from that MTOpt project before. And that's why I actually wanted to present MTOpt previously, because this is just using that same data, but with a very different method. And now you can get much more flexible behaviors. So in this video, in the lower right, you're going to see a snapshot of the goal. So this is basically the picture that's provided to the robot by the user. And in the top right, you'll see what the robot is currently seeing. And then there's a zoomed out view in the middle. So here, the goal image has the robot holding a bottle. So the robot understands that what that means is that it needs to pick up the bottle. Here it's holding a carrot. So it knows that it needs to go and pick up the carrot. Here it's holding the corn. So it goes and picks up the corn. Here it is holding the broccoli. So it goes and picks up the broccoli. Now, these are fairly simple. We're going to have something a little more complex. Here in the goal image, the carrot is lying on the plate. So it knows that what that means, that it needs to go and find the carrot, pick it up, and actually put it in the plate. Here, the banana is in the bowl. So it knows it has to go out and get the banana. And again, it's not getting any other reward information beyond just like binary success or failure. Did it match the goal or not? And this is all from the offline data. So in the online data, we don't need to label that. There's something a little bit more complex. That's to reposition the banana to be close to the carrot. And you can see it actually picks it up and moves it a few times to get the location just right. Same thing here. It actually picks up the carrot and actually tries to drop it a few different times to try to get the location correct and even get the orientation correct so that it matches the goal image. And just keeps trying until it gets close. Now, at this point, you might say, well, okay, specifying these goal images is probably kind of labor intensive. Like nobody wants to command a robot that way. So what's the point of doing all this? I think actually the real utility of these kinds of goal condition methods is that they provide a kind of unsupervised pre-training for RL. So remember, our goal is not to learn a universal policy that does everything. Our goal is to use prior data to get a really good starting point so you can very rapidly fine-tune to a new task. And this actually gets us that. So because all of your prior data can be used as offline data for training these goal condition policies, you can train your goal condition Q function with offline RL and then fine-tune with a task reward and much more limited data. The actual implementation actually doesn't do pre-training and fine-tuning. It actually does joint training with two heads. One head for goal conditioned RL, which uses all of the offline RL data, and one head that is task specific, but has much more limited data with the task rewards. And here the blue curve shows the version that has the actionable model's goal condition head, and the orange curve is the baseline that just learns the new task from scratch. And you can see that we're getting a lot of improvement in efficiency from including this self-supervised goal-reaching objective. So this kind of system, in a sense, does have at least partial answers to all three of the questions, although of course there's lots of room for improvement. It does do reinforcement learning using broad and diverse data sets in step 1. It leverages the starting point to rapidly adapt to new tasks in step 2, and it's a multitask system because every goal is essentially a different task. The last technical part that I'm going to go through fairly quickly to kind of to leave you off with some kind of more speculative directions is, well, can we, in the manipulation world, also think about inventing our own goals? So we have to provide this thing with data, but if we do have to collect our own data, how do we get the useful data in a new environment? We can think about automating task proposals, a little bit like how we did it in the navigation setting. So this is a method that we published very recently called VAL, Visual Affordance Learning. And the problem statement in VAL is to leverage prior data to explore a new environment by proposing likely goals, adapt to the new environment, and then carry out those user-specified goals. So very much like the recipe before, except now, instead of training the best possible initial model for performing multiple tasks, we're going to train the best possible model for exploring. And instead of fine-tuning from additional interaction for a specific task, we're going to actually invent tasks to practice in a new environment without any reward to fine-tune for whatever thing someone might ask us to do in that environment. So let's say that you have a prior data set of a variety of manipulation skills for your robot to practice, and then the robot is placed in some scene like this one with the shoe, and the user wants it to pick up the shoe. Okay, maybe it won't succeed on that right away because it's never seen a shoe like this. But if prior to being given the task goal, it's allowed a little bit of unsupervised interaction, maybe you can figure out that this shoe is something kind of interesting. Maybe it has some ideas about what to do with it, but it doesn't know exactly how, so it can practice manipulating the shoe a little bit so that it can be ready for whatever the user might command. So before this goal is issued, perform some unsupervised practicing in the new domain to prepare for likely downstream tasks. So I'll just skip over this part and explain the method. So the setup is that, like before, we have a prior data set of a variety of tasks, and we're going to actually learn two things. We're going to learn a behavior, a goal condition policy, just like in actionable models, but also an affordance model, a model that looks at the current state using a latent representation and predicts potential goals you could attempt here. So it's a model of affordance. It's a model of what can you do in this environment. And this is based actually on a conditional VQVAE model. So what you can see here in this example, the conditioning image has a pot and a lid, and the model predicts what could be done with this lid. So the images on the right are actually not real images. These are synthesized images from the model. And the model hypothesizes that it could pick up the lid, it could drop it on the pot, it could also drop it somewhere else. So these are like possible things it's imagining it could do. It might not know how to do them physically. So the idea is that maybe it's easier to imagine what could be done than to actually do it. But then it will practice these and figure out how to do it. So that's the online learning stage. And here's a video of this in action. So here we took the pot lid and we attached a weird object to the top that the robot hadn't seen before. So it succeeds at putting this lid on the pot about 37% of the time. That's just done for your visualization. So we didn't actually tell our algorithm that this is what the task is going to be. In the online training phase, we just asked it to propose its own goals, which you can see in the inset in the lower right. And then it's going to practice those skills, sometimes successfully, sometimes not. But in the process, it'll master the manipulation of this particular new thing in the scene, so that after we then give it the goal, it'll perform it with a much higher success rate. There are a few other tasks like this. So here, there is a drawer with a handle that the robot hasn't seen before. If we were to just tell it to close that drawer right away, it would succeed only about a quarter of the time. But if before giving it the goal image, we allow it to imagine possible outcomes, then it will practice closing the drawer. It actually does this pretty well because it has seen other drawers before, just not with that handle. So it can generate a goal image with a drawer closed and then go and practice it. The practicing, sometimes succeeds and sometimes fails, but it does give it enough additional experience in this environment that it will succeed on the task very consistently after the practicing phase. All right. So just to wrap up, I talked about these three questions, and I think that resolving these questions is really important to get scalable robotic learning methods that can really master both visual perception and the physical act of performing these tasks. I discussed these in the context of robotic navigation, manipulation in multitask settings, and even manipulation settings where the robot has to imagine possible things to practice. What else do we need? We need algorithms for these kind of offline learning with online fine-tuning. I didn't go into the technical details of the algorithms in this talk very much, but if you want to learn more about that, you can check out these two papers on offline RL algorithms. We need algorithms for meta learning and learning to explore. So I talked a little bit about learning to explore, but there's a lot more algorithmic depth there. And if you're interested in this, you can check out some work on meta learning that studies this. And of course, we also need the data sets. So I didn't really discuss where the data sets come from in great detail, but I think we as a community can advance scalable robotic learning by actually collecting shared data sets that we can use for this kind of offline training. We've taken some steps in this direction, but I think a lot more work there is needed. But to conclude, I think one message I want to leave you with is that addressing these challenges, if we can do it, will bring us closer to truly in the wild robotic systems that can generalize broadly, perform diverse tasks, and autonomously improve their performance without human involvement. And I think that there's some steps in this direction, but a lot more of the most exciting work has yet to be done. Thank you very much for listening. And also I want to thank the students that carried out this work, and I'd be happy to take some questions.
Thank you so much, Sergey. And if anyone has a question, please feel free to raise your hand. I got a question, Sergey. So so I think it's a really promising direction to use like prior data or like offline data to pre-train like a good enough model, and then to have more interactions to fine-tune this model. But do we know how good this like past interactions need to be in terms of like the quality of the expert policy, or the domain gap between the old and new tasks? And for example, like I would imagine in extreme case, if that expert policy always do some risky things or crash on the road, then that can actually backfire right during the RL phase. So what do you think?
Yeah, I think that's a really good question. I think that there's a lot more that we can do to understand the sensitivity of offline reinforcement learning algorithms to data quality. I mean, it should be a lot better than, for example, imitation learning, because the RL methods can improve over the best performance in the data. But at the same time, this is actually a lot of why I presented the recipe, not as one of using prior data to get a policy and then just like succeeding at everything, but as using prior data to train a starting point that can be fine-tuned rapidly. Because I think that whatever effort we take to robustify the skills that we get from offline data, ultimately, if you want the very best performance, if you want the robot to really clean your bathroom really, really well, then we need that fine-tuning phase. And I think that's what we see in for human learning too. Like people aren't necessarily incredibly proficient at every single thing. It's the flexibility, the ability to quickly figure out new things that kind of sets human intelligence apart from machine intelligence. So I think that in the long run, we just need the fine-tuning part to patch any holes, and we'll never fix all the holes purely with offline.
Yeah, thanks. That makes a lot of sense. I see more questions among the audience, but actually, since we are running just a little bit over time, and Sergey will come back at 4 p.m. For the panel discussion. So I guess if anyone has a question, feel free to come back at 4, or you can actually use our link to pose the questions, and we'll actually ask our speakers these questions during the panel discussion.